Hi, everyone. My name is Dylan Walter.
Hello, my name is Alejandro Porcar.
I am Diego Conterno.
And I'm Tyler Michaud.
We are Senior Design Group C, and our project is called the ADEPT, or Analog and Digital Effects Processing Technology. As engineering students, as well as musicians, our team has decided upon a senior design project based around audio engineering, music technology, and sound design. Throughout this project, we have been able to apply the engineering fundamentals we have learned throughout our respective undergraduate degrees into something we are passionate about. Closing the gap between technology and music, we are providing a new alternative for musicians who want to stand out and shape their sound in a unique way. We're providing a digital multi-effect solution that will have a creative impact not only on musicians, but also those with an interest in electrical and computer engineering. Since our project is open source, anyone with the necessary know-how can utilize our platform to develop any DSP audio effect that they could possibly think of. Next up, our objectives for the project. Our compact design is the perfect size to fit on any musician's pedal board alongside other music gear. Our pedal was designed to be as affordable as possible in order to compete with the many boutique guitar pedals available on the market today. Not only should an aspiring DIY enthusiast be able to afford all the components of our project, but it should also be easy to assemble and to use. With a simple user interface and parameter controls, the ADEPT is foolproof. On the more technical side of things, we designed our project to draw as little current as possible. This is important in order to maintain compatibility with the standard 9-volt, 100 milliamp pedal power supplies available today. We also made sure that we are only hearing the effects that our unit will apply to our instrument signal without any unwanted noise. The ADEPT has a signal-to-noise ratio of 15 decibels with clear signal quality. Last but not least, the ADEPT is reliable. By utilizing high-quality components and a strong metal enclosure, musicians will be able to rely upon our product to function as it should, even when performing in harsh weather conditions or when stomping on this effects pedal night after night. In order to ensure that our project has met all the necessary guidelines, we've assembled a project test plan. In this plan, we will be testing both the analog and digital aspects of our project's deliverables. On the analog side, we will test our circuit's input and output impedances, the power transient response of our linear voltage regulators, and our signal-to-noise ratio. On the digital side, we will demonstrate our codecs functionality by performing both a loopback test as well as a data transmission test. We will also demonstrate how data transmission works on our external flash memory module.
So for our input and output impedance test, we use an impedance analyzer to read the input and output of our buffers to see if they matched up with the values calculated in our small signal analysis. The buffer input needs a high input impedance, and the output buffer needs a low output impedance. This enables us to properly drive our signal through our pedal and into the amplifier. Calculations were sufficiently close to our measured value. Without these buffers, the sound of the guitar would appear darker and more attenuated. The buffers allow our sound to appear brighter and fuller. So for our power transient response test, we use an oscilloscope to observe the board stability when powering on and off. We measured the 9-volt input and the regulated 5-volt and 3.3-volt outputs. We specifically wanted to see if there was any overshoot or damping effects during power on, along with undesired ripple during power off. We also wanted to make sure that our power on time was fast enough to appear instantaneous. The total time our pedal took to completely power on was 80 milliseconds. For a signal-to-noise ratio test, we wanted a signal-to-noise ratio of about 14 decibels. To confirm this, we measured the magnitude of the signal and compared the ratio of the magnitude of the AC ripple along our signal path in logarithmic scale. We measured a signal-to-noise ratio of 14.92 decibels. Our measured signal-to-noise ratio was better than our desired value by about 1 decibel. A low signal-to-noise ratio can lead to bad sound quality, so it was important to confirm that our signal was strong enough to negate any noticeable noise.
Codec latency test. The goal for this test was to find out the magnitude of the latency between the input and the output signals of the codec. This test consisted of inputting a sine wave to the chip with a function generator and using an oscilloscope to display the two signals on the same timescale. We then used the oscilloscope cursors to measure the time difference between the peaks of both signals. We found out that the output signal had a small delay of 745 microseconds, which is an acceptable amount of latency, as most musicians with a trained ear cannot detect the latency under 7 to 10 milliseconds. Our codec data transmission test. We performed a series of tests to confirm that our codec chip was outputting its signals correctly when given a clock and an input signal. We used the oscilloscope to tap into some of the most relevant bits of the codec and display them. We first tapped into the LR clock and the bit clock of the chip. According to the datasheet, the chip transmits in frames of 32-bit words. For this reason, when displaying both signals, we wanted to observe that for every cycle of the LR clock, we will get 32 cycles of the big clock, which we confirmed. For the next test, we tapped into the LR clock and our data in pin, which is the output of the STM32 audio data into the codec. We wanted to check this time that each audio data sample fell inside each of the cycles of the LR clock. Flash memory data transmission test. First, we tested by writing and reading dummy data to and from the memory. Using this test, we were able to confirm that we can access the correct address by writing and reading to different blocks of memory. And we also made sure that our data is not getting corrupted during transmission by comparing the content of the receive buffer to the transmit buffer. Our second test consisted of writing audio data and coming from the codec to the flash memory. With this test, we proved that we can store our audio without getting any data loss when sending long streams of data. Our third test consisted of sending our stored data to the codec to reproduce the sound. We confirmed that we could reproduce the audio, but we did have some discrepancies that we will mention during our challenges section.
Now we're going to perform a little technical demonstration for you. We're basically just going to outline a couple different things, including the user interface, our LCD screen, parameter potentiometers, volume and tone controls, rotary encoder, on-off switch, tap looper switch, indicator LEDs. We're also going to demonstrate how our codec works, as well as a couple of our DSP effect implementations.
3.
All right, so here we have our current breadboard setup for our prototype. You see our input buffer and our output buffer that's going to our input and output jacks of our guitar pedal and amplifier. We also see our STM32 Nucleo board being powered externally via 5 volts. We have a 12.28 megahertz clock coming from this function generator, which is driving the codec. We have 9 volts coming in from the wall plug. And here you can see our sort of mock-up. We have the LCD screen displaying the effects parameters, the 3 parameter knobs, rotary encoder to select between different effects, volume and tone, on and off switch, and tap tempo switch. So here's the clean tone. And now we're going to engage the effect. Here's reverb. We've got delay. We've got a sort of pipe type setting. We've got a pitch shifter. We've got a compressor, subtle effect. We've got a distortion, which can get very loud, so we'll... That's about it.
Challenges. Improper voltage of level 5 volts was sent to the MCU, which has a max voltage of 3.8 via parameter control potentiometers, which resulted in hardware failure on our first PCB prototype. The ADC pop parameter jitter due to external clock. The issue was not resolved to its full extent due to the current state of our test bench. This is being on a breadboard and components not properly isolated. We expect the issue to be resolved when populating the new PCB. Otherwise, a quick fix would be through a firmware update. Codec MCU communication setup. We faced technical difficulties when trying to properly communicate the codec and the MCU. This was mainly due to a couple of points. The STM32 set has master, resulting in an unsuccessful data transmission. Clock configuration for the codec required an independent external clock to be set as master, and the STM32 has slave. 2. Adjusting the communication configuration of the I2S using DMA. 3. Implementation of a ping-pong buffer utilizing DMA interrupt callbacks. 4. Data decomposition from half words and recomposition to full words during the processing of samples was required. Codec and encoder interrupt in conflict. We were getting stuck in the encoder's interrupt when utilizing codec. The conflict was resolved when we compiled a new version of the code and rewired the system. Loss of codebase. Thanks to the version control, we were able to recover a great part of our progress. We were also able to reconfigure the system by reverse engineering the current breadboard setup. The solution also solved the codec and encoder interrupt conflict. Flash memory MCU communication setup. Non-blocking APIs affected writing to memory. Blocking APIs were utilized instead. We were able to read and write multiple times to different sectors of the flash memory without any conflict. However, we were unable to retrieve the data at a proper speed for playback. Intrapersonal relations. Stress and anxiety from the complications mentioned above gave rise to conflicts among the team. This was solved by doing in-person team meetings, constructive reasoning, and problem solving. We apologized and shook hands on it. Successful collaboration and teamwork. We set weekly meetings at least once per week, where we discuss progress, future objectives, roadblocks, and deadlines. Utilizing project management tools such as Notion, we were able to stay on top of deadlines and to track our progress. We use both Discord and WhatsApp to stay in constant communication.
We utilize sites such as When2Meet to schedule weekly meetings. We use Google Drive to share and store files, and we use GitHub for version control. Stakeholder feedback. Friends and colleagues provided some feedback, which helped with brainstorming for our project. However, we did not receive any professional feedback from sponsors or industry professionals. Project perseverance and team morale. Constantly overcoming technical challenges was a given. Personal goals and team goals. Motivation to see the project through and have it working. External support by friends, professors, and professionals in the industry. Team meetings and team bonding when working together and helping each other out. Our biggest lesson learned was the ability to work long hours without getting burnt out and unmotivated, while also being rigorous and detail-oriented.
Thank you.
Thank you.
Thank you.